that we don't waste time with my, it's fantastic.
And you always say next. Then,
yeah, please, next one. We will describe what we do with the sun energy. Next, please. This is a now will come picture, which is done by the astronomer Josef Klešek, and you see 180,000 terawatts we are getting from sun, and only 10 terawatts we have in economy. And sun heats our planet of 290 Kelvin or degrees. Next one. When we are on the outer layer of the planet, we will measure of our atmosphere. We will measure 1400 watts per square meter up to 13 watts per square meter, depending on the position of our Earth on its elliptical way around the sun. Next one. And there is a big difference between the incoming solar energy on sunny day. The vertical axis are watt per square meter we are getting on surface of the Earth, and the horizontal one is daytime. You see, when there is a clear sky, we are getting up to 1000 watt per square meter. When there is a cloudy, we are getting several times or order of magnitudes less. Next. This is a normal picture of my region, and what Christian showed, next picture, is a thermal one, and you see that the dry surface of roof have 53 degrees, and wet meadows, they have 29 degrees. Next. We can even check it using the thermocamera, next one, which was on the airplane or on the balloon. So in normal landscape, agriculture landscape, we have temperatures from 30 degrees on the full sunshine, like water, like wetland, like forest, up to 40, which is cutted meadow, or over 40, which is a road. Next one. And we can understand basic. So first, flux of solar energy can be measured in watt per square meter. Second, what we deal with is a latent heat of vaporization. In order to evaporate 1 liter of water, we have to add 2.5 megajoule divided by second in the hour, which is 3,600 seconds. We are getting 0.68 kilowatt hours, which is 0.7 kilowatt hours. We have to add the 1 liter of water, and then we have water vapor. Please mind that from 1 liter of water, liquid, we have 1,200 liters of water vapor. It's Avogadro law. So each evaporated liter of water has a volume of water vapor 1,200 liters. And we use capacity of capacity of car accumulator, which is 0.6 kilowatt hours. So what is happening around us is a huge transfer of solar energy. Next one. Here it is graphic on left, 1 liter. We add 0.7 kilowatt hours. We have more than 1 cubic water vapor, and very important, now somewhere water condensates back to water liquid. The energy is released and air drops. This is very important and very understandable. Next one. Let us have a look on the tree in the city. We measure with a simple device, which is quite correct, 877 watt per square meter, and surface temperature 51 Celsius. The instruments are quite cheap. Now we go, next one, now we go under the tree. The amount of incoming solar energy is 82 watt per square meter, and temperature is 27 degrees, 25 less. What we are able to do it also is to measure subflow, how much water goes through the trunk, how much water just now the tree evaporates. Please believe me that it was 20 liters per hour. So we will multiply 20 liters by a latent heat of 1 liter, which was 0.7. So the tree consumes 14 kilowatts for cooling. It is amount of energy which is hidden, which is latent, which disappears in water vapor. Photosynthesis takes just 0.2 kilowatt. So there is a huge process of cooling. Next one. We can, when we do it scientifically, we can compare what is happening with the solar energy on concrete, on field, on meadow or wet meadow. On right-hand side, there is a rate of evapotranspiration expressed in milligram per square meter per second, or as a latent heat flux in watt per square meter. We are looking at the right part. The green one is a wet meadow. The red one is a concrete. So a lot of energy goes to evaporation in case of wetland, and almost none energy goes into evaporation in concrete. Have a look on left. On left side, we see so-called sensible heat flux. What is the heat which is produced on the surface? A lot of heat is produced on concrete up to 400 watt, and not much heat is produced on the wetland. Next one. So we can say that we know roughly what is happening when 100 milligram of water is evaporated from 1 meter square per second. 240 watt per square meter is used, is hidden in the water vapor, and this will be released then as a dew or in the clouds. Photosynthesis, it takes maximum 10 watts. And for each one molecule of CO2, which is taken, several hundred molecules of water are evaporated. Next one. Now, we have a dry place. It may be parking place, or it could be just harvested meadow, 45 to 60 degrees. And then we have forest. The forest looks like that it wastes water, it evaporates. And the dry place is innocent, it cannot evaporate water. Please, next picture. However, there is a fast movement of warm air from the overheated dry surface. It is this red arrow, and it takes humidity from the forest or from the next open water. So then when we have such heated, high temperature dry surfaces, we lose 1 centimeter of water per day, and we say, oh, open water wastes. We cannot allow open water because it evaporates too fast. No, it's a problem with the overheated dry areas. Next one. Interesting is the distribution of temperature in forest. We say there is an inverse temperature. The forest has a bit higher temperature on top of the canopy and lower temperature down. So if you have a 30 meters high forest, it keeps water because the lower temperature is down and air is heavier there than on top. So crowns just interfere with the atmosphere and not the down. Please, next one. If we cut forest or if it is dry due to bark beetle, then we have very high temperature of this dead forest up to 60 degrees. Next one. And this is corn. Corn has, because it doesn't have any vegetables down or any wheat, it has soil temperature 40 to 50 degrees and top temperature 33. So there is a still flux of warm air from down up And this is way how we are losing water. Next. I was asked several years ago by William Mitch. He was long time the main editor of the Ecological Engineering, and you know him as the author of the wetland book. And he said, okay, what we did when we drained a lot of wetlands in United States. Please, next picture. And it was drained about 44 million hectares of wetlands in United States. So when we just multiplied this huge number by the latent heat we lost, because when evaporation stops, then we have release of sensible heat, which is real heat, which then goes into the atmosphere and makes mess. I hope next picture, yes. So 46 million hectares means 460,000 square kilometers. And when we just calculate with the shift of 200 watt per square meter from latent heat to sensible heat, then we have produce of heat 110,400 gigawatts, which is comparable with this 55 power stations we have. Next picture. Yeah, this is the big power station in my region, which produces 2 gigawatts of electricity. But when we drain large areas, we are releasing huge amount. We said for United States, 100,000 gigawatts. Next one. So human modification of landscape by deforestation, industrial agriculture, urbanization destroys the capacity of ecosystem to use energy for evaporation and light processes, equalize differences in temperature and air pressure. Then we have torrential rains, hurricanes, and so on. Next picture. And now just, I have a look on time, it's okay. So let us measure how much energy is coming. It is in form of short radiation, it is the RS. Then how much is reflected? And let us also measure flux of heat. Please, next. Next. Now, we have two situation in longest day, which means 20 June. One was in a sunny day, which was year 2017. The other one is also about 20 June, but cloudy day. And on the vertical axis, there is an energy flux in watt per square meter. On horizontal, there is a daytime. The black one shows theoretical amount of energy which would from sun, which comes under clear sky. You see on sunny day, the red one is the incoming solar energy. On cloudy day, we see that we have 10 times less. It's red on the right-hand side. The blue one is a reflected solar energy. You see it on the left-hand side. And the brown one, it is a heat flux from sensor to atmosphere. You see that the flux of heat is about 180 watt per square meter. And there is almost no fluxes to the heat from Earth to atmosphere when there are clouds. Next picture. These are temperatures on sunny day and on cloudy day. The most important is a blue one down, which is effective temperature of sky calculated from the flux of watt per square meter and Stefan Boltzmann law. The green one is the surface temperature of the ground. And you see that we have a big differences. Why not? in the sunny day and very small differences in temperature on the cloudy day. Next one. And now there is a March this year. We had very clear sky and we had a very nice weather. So this is this red curve which shows it's really measured. It's not model. How the solar energy maximum was 700. It's a March, and you see the blue one, which is the reflected solar radiation, and I show it in order that we realize what happens when there is a clear sky. It is the brown one. It's a flux of heat from ground to atmosphere up to over 150 watt per square meter. Next, please. And here are temperatures. So the effective temperature of sky is almost -40, and effective temperature of the, no, surface temperature of grass, it's a green one, is up to 10. Next one. So back, please. I thought I, so there is a very important thing, that the flux of heat in the sky is mostly controlled by humidity and by the clouds. And when there is a clear sky, we have a flux 150 watt per square meter. These are measured data. So we have to focus on the role of vegetation, role of land cover in the water vapor, clouds, rain, and so on. And next picture, and next one, I hope. There is a no one.
No, there's no one.
Oh, I have a bad anyway, I had there some books, some references that we do Erasmus project called Education for Plant Literacy, which we try to develop methods for teaching, because many things can be now shown as I tried to do. So thank you, and I apologize for the technical problems. Thank you. It's all.